Well, so far so good. Um, we're getting closer and closer to being able to fire this up again. Right, quick recap. The original 3-amp diodes from the cold driver boards have been removed and replaced by 50-amp bridges. That's one per cold driver board. Previous to this, I don't know why I've done that, but I've been referring to these bridges as 35 amp. They're not, they're actually 50 amp. But that 50 amp rating is under test conditions within which every bridge is mounted on a, I think it's a 6-inch by 6-inch copper plate, about 1.5 millimeters thick, all finned heatsink, or a plain copper plate. If it was a heatsink, it would be about 4.5 inches deep and made out of aluminium, not copper. Okay, now I've got that little thing out of the way. In my head, seeing as the heat sinking isn't the same on my implementation, in my head I've been fixated on this figure of around 35 amps for the heat sinking that I've used. There's no way I'm going to fill up this workshop with the test heat sinks that were used. I'd have nowhere to work. So the ballpark right now with the heat sinking that I'm using is around 35 amps. I don't think I'll be approaching anything like that, but as a requirement. Okay, all that's in place. The common grounds are all connected for the bridge DC negative. So the common grounds are the bridge DC negatives. The bridge DC positives are all connected to the positive power rail. Across those two terminals, that's the bridge DC negative and bridge DC positive, which is the power rail negative and the power rail positive, a 47K cap will be connected. What remains at the moment is the interconnects for the positive power rail for the cold driver boards are at the moment on their own bus, as it were, whilst the positive power rail for the bridges are on their own power rail. I just need to connect the two together via a simple wire. Looking at the circuit board, the main circuit board, this big piece of crap here, and that's what I'm looking at as I speak. All previous connections prior to the last test are still in place. That's okay. The 12-volt power going to the controller boards is in place. The 12-volt power that drives the MOSFET gates are in place, and the ground for that 12-volt supply is in place. That ground is separate from the coil driver or the power circuit ground. I'll say that again. The ground for the 12 volts that feed the MOSFETs is a separate ground to the ground that is found on the power generation side, which where the bridges are connected, so on and so forth. Right, now I'm hoping that makes sense. I will follow this up with a much more detailed explanation of the whole thing, and upload that to YouTube. But this is just as we speak right now. This is purely a bit of a rundown as I step back and rationalize what I've done, and hopefully introduce some sanity where I observe that sanity is lacking. I tend to do that a lot. Rationalize my work in this and other areas. Okay, so I'll start by bridging those positive rail buses, or bus bars, or whatever they're called. The Muller motor is connected to the board. This is the connection for the Hall effect sensors. These two here are the coil connectors. The coil connectors connect obviously the coils on the motor to the coil driver boards, and the Hall effect sensors connect to the logic side. Both sides, the logic and the power generation, are optically isolated. Their power supplies are isolated, their grounds are isolated. I tend to think of the logic side having a signal ground, whilst the power generation side has what might be called a chassis ground, or an earth, a true earth. Not necessarily a true earth as it happens, because that ground, the ground for the power generation side, ultimately gets connected to the negative post of the battery. And the positive post of the battery gets connected to the positive power rail. I don't know if a car battery is overkill, but I've got that ready to use, in addition to a rarely used 12 volts battery I bought recently at the time that I tested this last, which is a long time ago now, really, I guess. I don't think the heat sinks that came with these diode bridges were particularly well treated. Generally speaking, they are in good condition. They were obviously new, but I don't know if it's down to shipping or not, but two of them had a slightly bent fin, bent by as much as 1 millimeter out of whack. But anyway, let me pop out the chat on this here so I can see what I'm doing, while I can keep half an eye out on what people are trying to tell me. The last time I was broadcasting, I mean, I pulled a real long one, more than 36 hours awake to get to the stage. I left the workshop went inside, made a cup of coffee, sat down for a second, and immediately fell asleep. I just passed out like a light, just like that, leaving all the lights on and what have you. Not a good thing when that happens. Okay, less of the yap, get on with the work. I'll start by relocating 2 of these leads. Do just fine. Okay. Okay. Before I proceed further, could just want to do a continuity check. Of everything that I've done over here so far. Good. No shorts. Close those. Positive should be connected to positive. Yep, it is. On each one of these. About 0.4 ohms resistance from each diode bridge DC positive to the furthest positive power rail connection. Same thing, continuity test. I say continuity test, I'm actually measuring the resistance from all the DC negative to the furthest power rail negative or ground, to which it's ultimately going to connect. Again, I'm getting a 0.4 ohm reading. Yeah, that's passed with flying colors. Very consistent 0.4 ohm resistance between the DC output terminals of each diode bridge and the corresponding furthest point on the bus. Or right, next thing is to look at the resistance on the AC legs. Now, AC legs, I mean, this should work out just fine. It's AC again 0.4 ohms. Yep. I'm looking at the resistance between the AC legs on each diode bridge and the posts on each coil driver board, because those posts, those two terminal posts, actually connect the coils to each coil. So the two terminal posts on each coil driver board connects to a coil, positive and negative lead, and in parallel to that is the AC input legs on the diode bridge. I fail to make myself clear to myself sometimes. Well, I hope I'm not speaking too soon, but this is very consistent across the board so far. Good connections. Low resistance. Which means good contacts on the posts. Goes to show, really, I suppose, that you don't really have to over tighten these posts to guarantee a good connection. Of course, they are no substitute for direct soldering, but as needs may be. Now I do know I've double and triple checked the connections on each post, so you don't need any further tightening or further checking, assuming all goes well with these last couple of tests. Okay. That's good. So every terminal of every diode bridge has been tested for resistance to its corresponding furthest connection on the main board. The results are 0.4 ohms across the board. So that is not going to be a variable that varies, pardon the pun, as I progress with tests later on. Okay, what I'll do now is I need to connect the logic side, the power generation side to and from the Muller motor, the coils, the power rail, positive and negative side. That's all done apart from connecting a 47K microfarad capacitor across the positive and negative terminals of the power rail. Okay, there's the only thing left to do on that. Simple Simon stuff. What remains, though, is now to reconnect all the logic side. That's the two logic boards connected up to the Arduino. Yeah, I still think I'm using the Arduino for this, for the time being. Yeah, setting up the logic side now, and I'll do a separate video for that.